welcome students to our first unit on science. In this lesson, we will review the concept of science, the importance of data, as well as begin a discussion on scientific inquiry. Science is a systematic study of nature. It is a process of learning about the natural world through observations and experimentation. It involves understanding how things work and using evidence to support explanations about the world around us. Science aims to describe and explain patterns in nature, helping you to explore and learn about various scientific concepts and methods. In order to understand science, we have to understand what we mean by reasoning. There are two types, and the first one is known as deductive reasoning. Deductive reasoning was perfected by the Greek philosopher Aristotle. It begins with a statement called a premise, and the solution is derived from logical statements, which comes from a conclusion. An example of this is geocentrism, first proposed by the ancient Greeks using deductive reasoning around 380 BCE. Our premise is that the sun moves in the sky from east to west. Our logical statement is that the spot at which we observe this is stationary. Therefore, the conclusion is that the sun revolves around the earth. For the next 2,000 years, science was the domain of the astrologers and priests. Galileo revolutionized the scientific community by introducing a new way. Galileo argued that inductive reasoning, not deductive reasoning, was logical. The idea of inductive reasoning was first proposed by Galileo. Galileo suggested collecting specific information about a problem observed in nature. Then draw a conclusion based on the specific information that was observed, which is referred to as data. The resulting conclusion is considered the probable or most likely explanation for what was observed. An example of the use of inductive reasoning in chemistry would be the mixing hydrochloric acid with the base sodium hydroxide. In the resulting reaction, it is observed that heat, salt, and water are produced. Therefore, when any acid is mixed with any base, then heat, salt, and water is most likely going to be produced. Next, we will discuss the concept of data. In science, we must be able to measure what we see in some way. There are two forms of data known as quantitative data and qualitative data. The goal of gathering data is to be as objective as possible. Quantitative data deals with numbers and represented by all data which can be measured. Examples would be length, height, area, volume, weight, speed, time, temperature, humidity, sound levels, cost, and ages. Qualitative data deals with descriptive observations. It is data that is observed but not necessarily measurable. Examples of this would be colors, textures, smells, tastes, and appearance, such as being happy or sad. In some instances, scientists can convert qualitative data into quantitative data, but it can be very time-consuming. Let's compare the use of qualitative and quantitative data when observing a cup of coffee. A qualitative observation of the coffee could include that it has a robust aroma, it has a frothy appearance, it has a strong taste, and it is in a burgundy cup. A quantitative observation of the coffee could include that it's a 12-ounce latte. It is at a serving temperature of 150 degrees Fahrenheit, that the serving cup is 7 inches in height, and the cost of the coffee is $6.95. Next, we will discuss the area of experimental research. The first step in understanding experimental research is defining the term hypothesis. A hypothesis is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. When developing a hypothesis for an experiment, you must also include something called the null hypothesis. In the null hypothesis, you are stating that nothing will change in the experiment or that there will be no statistical significance in your given observations. This is the hypothesis of no change. For example, when conducting an experiment evaluating the impact of caffeine ingestion prior to testing, your first hypotheses, or H1, could be that if students are given caffeine before a test, then they will perform better. A second hypothesis, or H2, could be if students are given caffeine before a test, then they will perform worse. The null hypothesis for this experiment, or H0, would be that if students are given caffeine before a test, there will be no change in their performance. As we continue our discussion on experimental research, we will now look at the observational part of the process. In observational study, a researcher or student will conduct a laboratory procedure to observe natural phenomenon. This is commonly done in the classroom or laboratory setting to better understand laws and theories. Unlike an observational study, an experimental procedure is carried out to support, refute, or validate a hypothesis. They do this by demonstrating what outcome occurs when a particular factor is manipulated. Experiments rely on repeatable procedure and logical analysis of the results. Experiments typically include controls, which are designed to minimize the effects of variables other than the single independent variable. This increases the reliability of the results, often through a comparison between control measurements and the other measurements. The first variable to consider in experiments is the independent variable. It is a variable that stands alone and isn't changed by the other variables you are trying to measure. A good example of an independent variable would be age. A person's age cannot be changed by factors such as what they eat, how much they go to school, or how much television they watch. Another form of variable is the dependent variable. It is something that depends on other factors and could change because of various forms of manipulation. A good example of a dependent variable is test scores. A test score could be a dependent variable because it could change depending on several factors such as how much you studied or how much sleep you got the night before you took the test. Next, we look at the entire process of scientific inquiry. In order to understand the scientific method, you have to realize that the scientific method relies on observation. Because of this, you have to recognize that observations can be biased and that conclusions can be biased. As a result, the scientific method cannot determine absolute truth, but what is most probable or most likely. There is an old joke in science that the only absolute is absolute zero. Absolute zero is the coldest possible temperature that can be reached. When achieved, all matter stops moving. Since observations in science are very important, we now have to discuss what an inference is. Inferences are important because all scientists will make observations about an event. These observations are treated as facts and should not be open to interpretation. Unfortunately, scientists observing the same event can make different inferences of what they see. This is because a scientist's current knowledge and perspective affects their interpretation of what they observe. This chart demonstrates the difference between an observation and an inference. You observe that a plant is extremely wilted, and then you infer that reason is due to a lack of water. You observe that your car has stopped running. You infer that it stopped because it was out of gas. And you observe that the baseball team, the Red Sox, are leading their division. You infer that this is because they are playing well right now. In the laboratory setting, you record your observations such as did the reaction produce heat or gas? Or did it change color? You do not record your inferences. Inferences represent your conclusion about what occurred after you review all your observations and data. For example, did you observe a physical change in matter or a chemical change? Let's see another example of whether a statement is an observation or an inference. Statement 1. There is a representation of a face on one side of the coin. This, of course, is an observation, as we all can agree on what is seen. Statement 2. The Latin word Dei means God. This, of course, is an observation as well, since Latin is a known and documented language. Statement 3. The coin was made by deeply religious people. This would be an inference, since we have no real evidence that this is true. Statement 4. The date 1722 is printed on one side of the coin. This, of course, is an observation, as we all can agree on what is seen. Statement 5. The coin was made in 1722. This is an inference, as the date could also be of historical importance to whoever made it. Statement 6. The face on the coin is a representation of the nation's president. This, of course, is an inference, as we have no data to support that conclusion based on what we can observe. The thematic application test is a great example of the use of inferences. The TAT uses inference to evaluate a person's psychological state. This is done using a set of picture cards showing different scenes and situations, like people talking or someone feeling sad. When someone is administered the TAT, they are asked to look at these photos and create stories about them. These stories show how people feel, how they think, and how they relate to other people. The following 3 examples are typical of the thematic application test. The subject would be asked to look at them, and with no other information infer what they believe is happening in the picture. Next, we will be covering the concepts of scientific laws and theories. Unlike theories, scientific laws are not subject to change. Scientific laws are not theories that have been proven true. A scientific law is a description of a relationship or a pattern in nature. A law generalizes a body of observations. No exceptions have been found to a law. Scientific laws explain things or identify how they occur. Scientific laws do not describe them, or in other words, why they occur. A good example of this is Newton's law of gravity. Newton could use this law to predict the behavior of a dropped object, but he couldn't explain why it happened. It wasn't till later that Einstein explained how gravity worked by proposing his theory of mass bending the fabric of space. A scientific theory provides an explanation for a relationship or pattern in nature. Scientists first observe and identify laws. It is through these observations that they develop or create scientific theories. Scientific theories exist to help explain the natural world and are uncovered through scientific investigation. All scientific knowledge is subject to ongoing testing and revision. All scientific knowledge can be discarded or changed when new evidence justifies it. Scientists' knowledge can change when scientists reinterpret existing findings. It is not uncommon for there to be misconceptions about what is considered a scientific law. 2 examples are carbon dating and beneficial mutation. For carbon-14 dating to be accurate, one must assume the rate of decay of carbon-14 has remained constant over the years. Evidence indicates that the opposite is true and that changing the environments surrounding samples can alter decay rates. In regards to beneficial mutation, the known examples of beneficial mutation exist only at the microscopic level and have not been identified in more complex forms of life. Remember, when it comes to a theory, to be successful, the conclusion it represents must be repeatable. It must be derived using existing scientific laws as a basis, and the conclusion must be agreed upon by you or anyone. Non-scientific theories can be easily identified as they make no predictions, are untestable, and can't be falsified, which means they cannot be proven to be untrue. A good example of a non-scientific theory is the face on Mars theory. This theory proposes that the chain of events needed for life to arise on Earth is too complicated to have happened by chance, and that an alien intelligence must therefore have caused life to arise. The proof for this theory is the face on Mars. The basis for this theory is a picture taken of the Mars surface by the Viking orbiter in 1976. As you can see, this object on the surface of Mars does resemble a face. However, a more recent picture taken by the Mars Global Surveyor in 1998 shows that this is not the case. The proof for the non-scientific theory was just an optical illusion. There are 2 primary classifications for false science. They are phenomenon and pseudoscience. A phenomenon has no provable basis for an event or theory. For example, yawning is something you likely do every day, but oddly enough, scientists still aren't sure why. Pseudoscience appears as scientific truth, but is not testable. An example of this would be the science of phrenology, where people believe your skull shape can predict your intelligence. Another thing to be concerned about in science is confirmation bias. Confirmation bias is a tendency for people to favor information that confirms their preconceptions or hypotheses regardless of whether the information is true. As a result, people gather evidence and recall information from memory selectively and interpret it in a biased way. Here are two examples of confirmation bias. Sally is in support of gun control. She seeks out news stories and opinion pieces that reaffirm the need for limitations on gun ownership. When she hears stories about shootings in the media, she interprets them in a way that supports her existing beliefs. Henry, on the other hand, is adamantly opposed to gun control. He seeks out news sources that are aligned with his position, and when he comes across news stories about shootings, he interprets them in a way that supports his current point of view. Remember, in true science, your work must be objective and reproducible. Objectivity means that your work was determined by direct examination and without bias. As for reproducible, this means that all your results can be demonstrated by any individual following the same process or procedure. In addition, true science must also be falsifiable. This means that your theory can be proven wrong by new information. It must also be observable, which means that it can be measured or described either directly or indirectly. The important limitation regarding science is that if it cannot be tested, it cannot be probable or most likely. Also, that pure objectivity is difficult to obtain and requires diligence during the experimental process. Finally, your results must be able to be expressed in some form of mathematical relationships. On the subject of objectivity, an important concept is that of paradigms. Paradigms are a particular view or bias that someone has. It is the basis for the way they perceive themselves and their world. We all have different types of paradigms, which are shaped by where and how we grow up and who our friends and families are. Let's discuss two of the most common paradigms that exist in the USA. They are the evolutionary paradigm and the intelligent design paradigm. A person with an evolutionary paradigm would most likely agree to the following. All life came from inert matter. The physical universe is a result of a natural evolutionary process. Man is an accident of nature. There is nothing beyond our finite reality. The following universally recognized scientists all believed in an evolutional paradigm. Charles Darwin, who was the primary contributor to the theory of evolution and natural selection. Richard Feynman, who developed the theory of quantum electrodynamics and the physics of superfluidity. Steven Weinberg, who discovered electroweak forces in relation to electromagnetism. Francis Crick, who discovered the structure of the DNA molecule. And Carl Sagan, who pioneered exobiology and was an authority on astronomy and astrophysics. On the other hand, a person with an intelligent design paradigm would agree to the following. There is a supreme intelligent being or beings. He or they are the creator of all things. He or they makes known to us the basis for all understanding about creation, the earth, and our purpose in life. The following are well-respected scientists who held an intelligent design paradigm. Nicholas Copernicus, who put forward the first mathematically based system of how planets go around the sun. Sir Francis Bacon, who establishing the scientific method of inquiry based on experimentation and inductive reasoning. Galileo Galilei, who developed a controversial theory on the solar system. Isaac Newton, a genius and innovator in optics, mechanics, and mathematics. Gregor Mendel, who developed the mathematical foundations of genetics. Robert Boyle, who conducted groundbreaking work on the understanding of gases. Remember, a true scientific process does not have to be affected by paradigms, and anyone can be a good scientist regardless of their paradigms. Another interesting area in science is related to the principle of limited sloppiness. This principle covers fortuitous or accidental discoveries or events which occurred inadvertently but were recognized as discovery by the scientist involved. One example involves Alexander Fleming, who noticed that a mold had contaminated his flu cultures in the lab. This was attributed to his lab assistant eating a sandwich while preparing the cultures. Particles of bread fell into the cultures, which provided a medium for the mold growth. He realized that the area around the mold was clear of infection. He received a Nobel Prize for discovering penicillin. Swiss engineer Georges de Mestral found burrs clinging to his pants and also to his dog's fur during a hike in the mountains. On closer inspection, he found that the burr's hooks would cling to anything loop-shaped like woven material or matted hair. He then artificially recreated the hook and loop system. The result was Velcro. Another interesting incident involved Konstantin Fahlberg. After a hard day of working with coal tar, he came home and, without washing his hands, grabbed one of his wife's dinner rolls and bit into it. It tasted sweet. He asked his wife if she had been doing anything different with the rolls. She hadn't. He had gotten coal tar on the roll. Fahlberg had discovered the first sugar substitute, known as saccharin, which is commonly referred to as sweet and low. Lastly, we have John Pemberton, a pharmacist who just wanted to cure headaches. Pemberton used two main ingredients in his hopeful headache cure, which was coca leaves and cola nuts. When his lab assistant accidentally mixed the two with carbonated water instead of regular water, the world's first Coke was the result. Our last discussion will be a brief review of the different types of branches in the field of chemistry. The first major branch is known as inorganic chemistry. This is the study of all the no elements other than carbon and their compositions. Next, we have organic chemistry, which is the study of all elements containing carbon. Another important area is biochemistry. In biochemistry, scientists study the chemical process in living things. Next, we have nuclear chemistry. This is a field of study that focuses on radioactivity, the nucleus, and the changes that the nucleus undergoes. Finally, science is broken down into two vocational areas. The first is pure science, where scientists pursue scientific knowledge for the sake of finding out new facts about matter. It is the science of discovery for discovery's sake. Lastly, we have applied science, where scientists pursue knowledge for the sake of creating useful products to make our lives and this world a better place. This concludes our first unit on science, where we have reviewed the concept of science, the importance of data, and discussed the process of scientific inquiry.